Hi everyone, let's have the last part number 5 of chapter 2. So here we are going to have a model for reliability and it's based on an example from the textbook. So here we have a milling machine which has 3 different bearings that fail in service. Okay, the description of the life of each bearing is identical. It doesn't mean that the useful life of the 3 bearings are exactly the same. No, it's not. It's not the case. I mean, here, the useful life, the value of the useful life could be different for the 3 bearings, but all they're coming from an identical distribution. So here we have random variables, right? Random variable for each specific bearing, and the distributions will be identical for all 3 bearings, okay? And when a bearing fails, the mill stops, okay? And a mechanic is called to install a new bearing. So the delay time for the mechanic to arrive varies randomly. And so we have a random, let's say somehow lead time, a delay time here actually, in order to the mechanic arrive the system to replace the bearing, okay? And during this time, machine is not working, right? So we call it as a downtime of the mill machine, right? And the cost of the cost of the mill downtime will be $10 per minute. So we are going to actually lose $10 per minute for the downtime. And the cost of new bearing is $32 per bearing. And the cost of mechanic will be $30 per hour. Okay, so the time of change of one bearing, these are constant. These are constant, and if the mechanic is going to change just one bearing, then it will take 20 minutes. Okay, but if the mechanic is going to replace 2 bearings, then it will take 30 minutes and 40 minutes for 3. So these are not random, these are actually constant. Okay. And the engineering team has proposed a new policy now. So we have this current system. In current system, anytime that we have a failed bearing, we'll call the mechanic, and mechanic will replace that failed bearing. Okay, and it takes time, a delay time in order to mechanic to be in place, and also the time of changing or replacing that bearing. Okay, so yeah, and this is our current policy, but the engineering team has proposed a new policy. Replace all 3 bearings whenever one bearing fails. So when we have a failed bearing and we have called the mechanic, then the mechanic will replace all 3 bearings. I mean, the other 2 are working, right? But we replace them as well. So this is the new policy, okay? Management needs an evaluation of the proposal using total cost per 10,000 bearing hours, okay, as the measure of performance. So compare current engineering policy versus the proposed one to see which one is better in terms of our performance measure and the costs, okay? So here's the data that we have. The bearing life in hours, it could be 1,000 hours, 1,100 hours, up to 19 hours in 100 units, okay? And here we have the probabilities and also the CDF that we have calculated, okay? So this is a discrete distribution that we assume for the useful life of the bearings, okay? And the delay time for the mechanic in order to be in place in minutes, it could be 5 minutes, 10 or 15 minutes with these probabilities and the CDF, okay? So these are our assumptions here. We are going to simulate the system for 15 bearing changes, okay, for all 3 bearings. So this means that we're going to have 45 replacement or changes in total, right? So in the current policy, we will simulate the system for 15 changes for each bearing. So in total, we will have 45 changes, 45 replacement. And also in the proposed policy, we are going to consider 15 change cycle. And at each cycle or at each set, we'll replace all the 3 ones, right? Again, we'll have 45 bearings replacement, okay? Two bearings may not fail at the same time. Yeah, I mean, in terms of the probability, it's too rare. The probability could be very low in order to have this case, okay? And bearing lives is in 100 hours, so it could be 10, 11, up to 19 minutes, okay? Where we assume that each minute here is 100 hours. Okay. Sorry, not in minutes, in hours. So 10 hours up to 19 hours, and we assume that 1 hour here means 100 hours. Okay, and the changes time are in minutes. Okay, so for the notation here, we define Bij as the life of ith bearing change jth time. So since we are going to have 15 changes, 15 replacements, so at each replacement, we need to consider a useful life for that bearing, right? So we will generate that from this distribution. So here we need to define Bij, okay? And BR will be the bearing here. So for the current policy, the Dij means delay for the mechanic to arrive and change ith type bearing, which has failed for the jth time, right? But for the proposed policy, we'll have Fk, I mean time between failure j minus 1th and jth set of bearing, right? And Dj here, it will be for the jth set of bearing, not for a specific type of bearing, okay? So let's see how we implement this model in Excel. For the current system, let's say at first we set j equals to 1, and then we generate the life of jth bearing, I mean jth replacement for bearing 1, 2, and 3. So we'll have these parameters here, B1j, B2j, and B3j. These are the useful lives for the 3 bearings, right? And then generate delay for 3 individual bearings. So yes, since we are going to replace the bearings individually, so we'll have D1J, D2J, and D3J, right? The delay for the mechanic. And then if J equals 15 for each bearing, I mean in total, then we will terminate the simulation, okay? Other than that, we will go to step 2 and we'll repeat the steps 2 to 3, okay? And then we'll compute the total cost. So that's it. That's for the current system. For the proposed system, again, we set J equals 1, and at this stage, for the jth set of bearing, we generate the time between failure, which will be the minimum between the useful lives, right? So we have the useful life for B1 for bearing 1, bearing 2, and bearing 3, and the minimum between these 3 will determine the time for replacing all 3 bearings, right? And then we generate the delay Dj for that replacement, and now again we check the stop condition, and that's it. And then we compute the total cost here. So the total cost would be something like this at the end of the simulation. As you see here, the cost of bearing is exactly the same between the two policies, right? I mean the purchase cost of bearings, because in both policies we are going to replace 15 bearing of each time. So in total, we'll have 45 bearings replaced. So if we multiply 45 by 32, 45 times 32 to the cost of each bearing, then it will be $1440. So this is the total cost of just purchasing the bearings, okay? But the cost of delay, as you see here, is different. The cost of delay for the current policy, it's just a number here. For example, it's just about 3,500, but for the proposed, it's about $1,150. So as you see here, there's a considerable difference between these two, and it makes sense because in the current system, we are going to have 45 delays. I mean, we will call the mechanic for 45 times to come to our system and then replace one bearing. But in the proposed system, we will call the mechanic just for 15 times. And at each time, the mechanic will replace all the 3 bearings. So this is the difference. And as you see here, the main difference between the current and proposed system is in terms of the cost of delay. And also the cost of downtime, right? Again, they should be different, right? And the cost of mechanic, again, since we have actually less time in the proposed system in order to have the mechanic, so again, the cost of mechanic will be smaller, lower in the proposed than the current one, right? And as you see here, we have the total cost, and since we're going to actually consider the total life, so for the total life for the 45 bearings, in the current it will be, let's say, 60,000, but in proposed it will be less, for example 52,200. Yes, it makes sense because in the proposed we're going to replace 2 bearings at each time that they are still working, right? They are still working, but we will replace them. So in total, the useful life, I mean the total life for 45 bearings in proposed system will be actually shorter than the current system, okay? And so because of that, we are going to calculate the cost per 10,000 bearings hour. So this is 10,000 bearings hour, okay? Hour. So, and as you see here, we have 2,000, sorry, $2,398 for the current system and $1,703 for the proposed systems, okay? So yeah, in the simulation model that we are going to have in Excel, we need to calculate these measures by the replications and the number of actually runs that we need to have. Then at the end, we can compare the 2 systems to see which one works better, okay? So as a discussion here, we saw that the proposed policy seems to have a significant impact on the cost, so it will bring us a significant saving, right? But how reliable is the results achieved? So in order to be more confident on the results, we need to increase the number of bearings, or we can increase the number of replications, right, in order to decrease the impact of randomness, right? So, and how significant are the proposed results? In order to answer this question, here in this chapter, we just can consider the average cost, for example, and by having a number of replications, then by having that replications, we can calculate the average cost, for example, and then we can compare the 2 systems by that average cost. But in chapters, I think 11 and 12, in those 2 chapters, we will see how we can actually conduct a statistical analysis in order to make more confident and more reliable insights, okay? Or, for example, we can consider continuous distribution of failure time instead of having the discrete one that we had in our example. For example, we can assume a normal distribution for the failure time. For example, a normal of 10 10 here means 100, so it means 1,000, right? 1,000 hours and 200 hours as the standard deviation, for example. Okay, so maybe by having a continuous, we may have better estimate, and it's also easy to model. Okay, so the rest of the models here that hitting a target and estimating the distribution of the lead time, demand, which is a Monte Carlo simulation, and a project network, activity network. For these three models will be covered in the tutorial session. So Asal will review all these three models in tutorial session. Okay, so that's it. We are done on this chapter. You can study chapter 2 of the main textbook, and also you can see the spreadsheet models in Learn. Actually, I have a folder in Learn for BC and N spreadsheet models. Okay, so and that's it. We're done on this chapter. In the next chapter, chapter 3, we will go with the principles of the simulation, and then there we will follow the approach of discrete event simulation. Approaching the time for the events instead of tracking each customers or each parts one by one. Okay, so the main concept of the simulation will be, I can say, started in chapter 3. Okay, so let's see how it's different than this approach in this chapter that we track each customer or each part individually. Okay, and that's it. Thank you.